This is the Honors Geometry Semester Exam Review for Unit 2, Topic 1. Question 42 states, in the figure to the right, line segment DE is parallel to line segment BC. CE is the length of 2AD, AE equals 8, BD equals 9, and BC equals 18. The first thing it wants us to do is prove that triangle ADE, so this little triangle right here, is similar to triangle ABC. So since we're going to do a proof, I'm going to make my two columns, and I'm going to have my statements and my reasons. So step 1 is going to be that DE is parallel to BC, and my reason is that this is given. Now, there's a couple different ways that you can prove this. Because we've got parallel lines, we know when it's cut by a transversal that corresponding angles are congruent. So we can prove that angle B is congruent to angle EDA, and angle C is congruent to angle DEA. So I'm going to put angle ADE is congruent to angle ABC, and I'm going to put angle AED is congruent to angle ACB. My reasons for both of these are going to be the same. They're going to be the corresponding angles postulate. So I'm going to write that for both. If you want, you can write out what this means in words instead, which would be that if parallel lines are cut by a transversal, then corresponding angles are congruent. Now, I've got an optional step that you don't have to do if you've written these, but let's say you only wrote one of these statements. Another angle that you can prove congruent is going to be angle A congruent to itself. So I could write angle A is congruent to angle A, and my reason would be the reflexive property of congruence. However, I absolutely do not need this step, but this might be one of your two angles that you prove congruent. Once we've proven two of the angles are congruent in each triangle, we can prove that triangle ADE is similar to triangle ABC. And the reason is going to be because of the AA similarity postulate. And this says that if we can prove that two angles are congruent, then we can prove that these triangles are similar. Next, we're going to determine the length of AD. So looking at this picture, I know that AD is right here, and I've just proven that this triangle is congruent to this. So I can set up proportions relating corresponding sides together. One type of proportion I can set up is AD over 9 equals AE over EC. This is called the side splitting theorem. So I know that if there is a side parallel to the base that splits the two other sides of the triangle, then I know that these two parts are proportional to each other. So AD over 9 over BD is going to equal 8 over EC, which is 2AD. I'm going to cross multiply, and that's going to give me AD times 2AD equals 9 times 8. Well, AD times 2AD is 2AD squared, and 9 times 8 is 72. So I next need to divide by 2, and I'm left with AD squared equals 36. If I square root both sides, we know that AD is going to equal 6. Part C asks us to determine the length of line segment DE. So I want to find the length of this. So I can set up proportions relating the small triangle to the big triangle. I can take either side and relate a side with the base with the side of the bigger triangle and its base. So a proportion I can set up is AD over DE, which is the base of the small triangle, equals AB over BC. Well, things we know. AD is 6. DE, we don't know. That's what we're trying to find. AB is 9 plus 6. And BC is 18. So I'm going to cross multiply, and I'm going to get 6 times 18 equals, so I know 9 plus 6 is 15, so it's going to equal 15 times DE. Well, 6 times 18 is 108, which equals 15 DE. And if I divide both sides by 15, I get 7.2 is the length of DE. So we know this length right here is going to be 7.2. Question 43 says, Jory wants to measure the length L, right here, of a pond. The figure below shows the measurement she will use to determine the length of the pond. In the figure below, line segment AE and line segment BD intersect at point C. So we're being told that these are two intersecting lines, which also then tells us that this angle must be congruent to this angle due to vertical angles. Part A asks, which similarity postulate or theorem may be used to prove triangle ABC, so that's this triangle right here, is similar to triangle EDC, so this triangle right here. Well, we have 3 different similarity postulates we can use. Side, 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 but we can't use that because even though 50 and 25, 20 and 40 are proportional, we don't know side L, so we can't use side, side, side. We also know angle, angle, but the only angle we know is this. We do not know that these are parallel, so I can't prove alternate interior angles. However, the third one is side, angle, side, which is something that we have. So we're going to use the side, angle, side similarity postulate to prove these triangles are congruent. And we can prove that because 50 over 20, that's hard to read. 50 over 25, we need to see, is that equal to 40 over 20? Well, 50 over 25 is 2, 40 over 20 is 2, so we know that those sides are proportional. Part B asks, what is the length L of the pond? Show how you determined your answer. Well, I'm going to set up a proportion. It doesn't matter which corresponding sides I use. I could use 25 and 50 or 20 over 40, but I'm going to relate it to 30 and L. So I'm going to set up 20 being the small triangle over 30, which is AB, and that's going to be equal to 40, which is the corresponding side for the big triangle, over L, which is what we're trying to find. Well, if I cross multiply, I get 20L equals 30 times 40. This means 20L equals 1200. And divide both sides by 20. We know that L equals 60. And we got to use our units, so 60 feet. So the length of the pond is 60 feet. Question 44 says, if two figures are similar, then corresponding sides are blank and corresponding angles are blank. Well, the definition of similarity says the corresponding sides are proportional and our corresponding angles are congruent. This is what it means for figures to be similar. So proportional and congruent. In question 45, we're told, in the figure below, triangle QRS, so that is this triangle right here, is similar to triangle QTU. So the first thing we're asked is to prove, just straighten that out, prove that RS is parallel to TU. So since I'm asked to do a proof, I'm going to make my two columns. I've got statements on the left-hand side and reasons on the right-hand side. So the first thing I know is that triangle QRS is similar to triangle QTU, and that is because it was given. Another thing we know is that by the definition of similarity, corresponding angles are congruent. So angle QRS is going to be congruent to angle QTU. You could also say angle QSR is congruent to QUT. Doesn't matter which one, but you just need one. So I'm going to say angle QRS is congruent to angle QTU. And this one is using the definition, kind of like CP/CTC, but with similarity. And we are going to have to write it out. So corresponding angles of similar triangles are congruent. Since we've proven that these angles are congruent, we know by the converse of corresponding angles postulate that these lines must be parallel. So we can go straight into proving that RS is parallel to TU. And the reason for that is the converse of corresponding angles postulate. If you want to write it out in words, you can say something like, if two lines are cut by a transversal so that corresponding angles are congruent, then the lines are parallel. Finally, we're asked to complete the proportions. QS, so that's right here, over SU equals blank over RT. Well, this is the side-splitting theorem, so if QS over SU, then it must be QR over RT. So this is going to be QR. The second one actually has a mistake. It shouldn't be RT, it should be QT. And this says that if QR over QT, so the side of the small triangle over the side of the large triangle, is RS, the base of the small triangle, so it should be over the base of the large triangle. So this is going to be RS over TU. Question 46 says, the figure below shows triangle BCD. Triangle B', C', D' will be the image of triangle BCD after a dilation with center B and a scale factor of 5. Complete the statements using the item bank on the right. The point B' will be the same point as point blank. Well, since this is the center of dilation, we know that our triangle is just going to get 5 times bigger. But B and B' are still going to be the same point. So the point B' will be the same point as point B. C'D' will be blank to CD. One of the things that we know about similar figures is that parallelism is one of the properties that's preserved. So C'D' will be parallel to C line segment CD. Finally, the perimeter of triangle B', C', D' will be blank times the perimeter of triangle BCD. Well, since we're talking about a scale factor of 5, this side length is going to get 5 times bigger. This side length is going to get 5 times bigger. And this side length is going to get 5 times bigger. So whatever this perimeter is, it's going to be 5 times bigger. Question 47 says, on the graph below, quadrilateral ABCD has been dilated, with the center of dilation the origin, then translated down 6 units to create quadrilateral A', B', C', D'. So we're given this picture, and we're asked, what is the scale factor of the dilation? Well, if you're ever able to, and you've got a horizontal and vertical line, in this case we have a horizontal, that's the easiest one to measure. So we can see that this is a total of 4 units, and this is a total of 6 units. So we know that our pre-image, DC, has a length of 4, and it's going to be multiplied by some scale factor to get a length of 6. So DC times some scale factor is going to give us D', C'. Well, if we solve for K, divide both sides by 4, K, which stands for scale factor, is going to equal 6 over 4, which equals 3 over 2, which also equals 1.5. So any of these answers, 3 over 2, 1.5, will give us the scale factor of the dilation. Part B says, what is the ratio of the length of AB to the length of A', B'? Well, we know that we're comparing the length of 1AB to 1A', B'. We also know that 1AB compared to 1A', B', we know that A', B' is 3/2 the length of AB. So really all I've done is I'm comparing AB to A', B', but I know that A', B' is 3/2 the length of AB. So this tells me that I've got an AB compared to 3/2 AB. If I multiply both sides by 2, I have 2AB compared to 3AB. Finally, if I divide by AB, I'm going to be left with a ratio of 2 to 3. So the ratio of the length of AB to the length of A', B' is 2 to 3. For every 2 line segments of AB, we will get the length of 3 line segments of A', B'. Finally, part C says, how are the measures of angle A and angle A' related? Well, since we know that there was a dilation, we know that the quadrilaterals are similar, and so one property of similarity is that angles are congruent. So we know that the measures are equal. The angles are congruent and the measures are equal. Question 48. Triangle ABC is shown on the coordinate grid below. So we're given this coordinate grid. Triangle ABC is to be dilated by a scale factor of 3 with the center of dilation, the point P, -5, -6, to produce triangle A', B', C'. Part A says, on the coordinate plane above, sketch triangle A', B', C'. Well, we know that we're going to scale factor of 3. So K is going to equal 3. And it's going to be from this point. So when we move in this distance, we're going 3 distances of this from point P. We're going to be going 3 distances of this from point P. And we're going to be going 3 distances of this from point P. So let's look at A first, because that's the easiest. When I look at P to A, I see that this is a distance of 4. So that means I'm going to go another 4 units up. I'm going to get a point there. This is a scale factor of 2. 1, 2 distances of 4. Since we want a scale factor of 3, I'm going to go up another 4, and this is going to be my A prime. It's at -5, 6. So if I look at B, to get to B, I'm going up 1 and over 3. So I'm going to continue that trend and go up 1 and over 3. We're going to get a point right here. That is a scale factor of 2. So again, I'm going to go up 1 and over 3. And I'm going to get my next point, which is B prime, here. This is going to be the point for -3. Finally, to get C, I'm going to go up 4 and over 4. So this is 1. So up 4 and over 4. I'm going to have my next point right here. And I'm going to go up another 4 and over 4. And I'm going to have my next point, which is C prime, right here at 7, 6. We can also see this because this is a distance of 4 from A to C. So I can go a distance of 4, a distance of 4, and a distance of 4. So we can see there would be a point there, there would be a point there, and we've got a scale factor of 1, 2, 3. So connect these points, and there's our triangle A prime, B prime, C prime. The next question is, what is the ratio of the perimeter of triangle ABC to the perimeter of triangle A prime, B prime, C prime? Notice it's not asking you what the perimeter is, it's asking for the ratio. Well, this is our ABC, so let's say it's got a perimeter of 1. We know that this length is 3 times larger, this length is 3 times larger, and this length is 3 times larger. So our perimeter of A prime, B prime, C prime is going to be 3 times larger than my original perimeter of, let's say, 1. Therefore, we are going to have a ratio of 1 to 3. And this is all because the scale factor is 3 times, or it's 3. Finally, part C asks us, is there a sequence of rigid transformations that will produce the same result? As we see, this A prime, triangle A prime, B prime, C prime is 3 times larger. So there's not going to be a sequence of rigid transformations because it's bigger. The size is physically changing. A shape can't get larger under a rigid transformation because rigid transformations preserve size and shape. So again, no, there is not. This is because this result is 3 times bigger than triangle ABC, but rigid transformations preserve size and shape. A shape can't get larger under rigid transformation because rigid transformations preserve the lengths, which is what indicates the size. Question 49 says quadrilateral ABCD has been dilated. The dilation results in the quadrilateral A prime, B prime, C prime, D prime. So this is our original pre-image, and this is our dilated image. Part A asks, what is the scale factor of the dilation? So one of the things that we can do, since we don't have any horizontal or vertical lines, is we can look at the slope from one set of points that makes up a side in the pre-image. So I'm going to look at points A and D, and I see that going from D to A, I'm going up 2 and to the right 2. So if I went from D prime to A prime, we're going to see how many times we can go up 2 and over 2, up 2, over 2, up 2, over 2. So I see 1, 2, 3. So my instinct is to say that the scale factor of the dilation is 3. However, I'd like to double check. So let's look, for instance, between B and C. Here we're going up 3 and over 3. So if I go from C prime, I'm going to go up 3 and over 3, up 3 over 3, and then up 3 and over 3. 1, 2, 3. So the scale factor of the dilation is going to be 3. The next thing I'm asked is, what point is the center of dilation? Well, in order to figure this out, we have to connect our image and our pre-image points. So A and A prime are connected, D and D prime are connected, C and C prime are connected, and B and B prime are connected. We want to extend the lines, though, through the points, because the point of intersection of these 4 lines is going to be where the center of dilation is. And I can see just visually, again, it's going to be somewhere over here. So if I connect these, I've got D and D prime, A and A prime. Sorry, without a ruler, this is going to be a little imprecise. C and C prime, and B prime and B. And what I see is that they pretty much intersect at this point, and that is going to be our point. That's the center of dilation. This point happens to be 5, 8. You want to make sure that you do this with a ruler because it will be more precise that way than my freehand. But that's how you find the center of dilation. Question 50 says pentagons ABCDE and FGHIJ are similar. We're going to find the value of x first. So remember that the order here matters. So AB corresponds with FG, BC corresponds with GH, CD corresponds with HI, DE corresponds with IJ, and AE corresponds with FJ. I personally recommend that you write those in just to help you picture it. So for instance, FG really corresponds with AB, GH is BC, HI is CD, IJ is DE, and JF is AE. This is going to help us write our proportions with our corresponding sides. So I need to find the value of x, which means I need to use CD in mine, and I need to use another side that I already know. So I'm going to use BC. So I'm going to make a proportion of BC over CD, and that's going to be equal to GH, because that's what corresponds with BC, and HI, because that's what corresponds with CD. So BC is 10, CD is 15, GH is 12, and HI is x. I'm going to cross multiply. I'm going to have 10x equals 15 times 12. Well, 10x then equals 180. Divide both sides by 10, and x is going to equal 18. My next part is asking me to find the value of y. So again, I need to use, with this first figure, I need to use ED as part of it, or DE. So I'm going to have, let's say, BC, because I know from this first problem, BC and GH are 2 numbers that I know. So we'll set up a proportion of BC over DE, and that corresponds with GH over IJ. So BC is 10, DE is Y, GH is 12, and IJ is Y plus 1.5. Using this proportion, again, I'm going to cross multiply. So I'm going to be multiplying my 10 by the expression Y plus 1.5, and I'm going to have that equal to Y times 12. Well, if I distribute, this is 10y plus 10 times 1.5, which is 15, equals 12y. I want to bring all my y's to the same side. So I'm going to have 15 equals 2y. Divide both sides by 2. 15 divided by 2 is 7.5, and that's going to equal y. Question 51 states, Jack wishes to find the height of a tree. He puts a stick into the ground and uses the tree's shadow to take some measurements. The figure below shows his measurements. Note that the figure is not drawn to scale. So we want to determine the height of the tree. What I can see is that we've got one big triangle and one small triangle. They both share this angle, and they're both right angles, so they must be similar. If they're similar, then their side lengths, their corresponding side lengths are proportional. I always recommend that you draw pictures to help decipher the information. This is my big triangle, this is my small one. Well, I know with my small one, my height is 5 feet, and my shadow is 9 feet. I'm trying to find the height of my tree. And the length, don't get fooled, is 135 plus 9. And this equals 144. So I can set up my proportion. H over 144 equals 5 over 9. Remember, corresponding parts need to be together, but this proportion can be written in 4 different ways. It could also be written as H over 5 equals 144 over 9, or the reciprocals. I'm going to cross multiply and get H times 9 equals 144 times 5. This gives me 9H equals 720. And when I divide both sides by 9, I get H equals 80. Don't forget your units, so it's actually 80 feet. The height of the tree is 80 feet. Determine the distance from the tip of the tree's shadow to the top of the tree. The tip of the tree's shadow is right here, so this is the tree's shadow, to the top of the tree. So I'm going to be finding this length, which is the hypotenuse. So if I draw my picture again, I'm going to have the height of the tree, which I now know is 80 feet, and the length of the shadow, which is 135 plus 9 feet, which gives me 144 feet. I want to find C. We're going to use Pythagorean's theorem, which says a squared plus b squared equals c squared. And so a squared is going to be 80 squared. B squared is 144 squared equals c squared. 80 squared is 6,400. B squared is 20,736. And that's going to equal c squared. If I add these two numbers together, I get 27,136 equals c squared. And to get c by itself, I need to square root both sides. Technically, this should be plus or minus, but because we're talking about a length, we know it's only going to be the positive answer. And therefore, c is going to equal 164.73 feet. This is a rounded answer, so please make sure you round correctly. Question 52 says, draw examples of two triangles that are similar by each similarity, postulate, or theorem. So part A says, draw examples of two triangles that are similar by SSS similarity. So we know we're going to have two triangles. They don't need to be drawn to scale, but we know that with SSS similarity, all three sides are proportional. So the examples and your answers for this are going to vary widely. But let's say I pick sides for one triangle, and I say this is a length of 3, this is a length of 4, and this is going to be a length of 5. To do this correctly, I'm going to pick a scale factor, let's say 3, and I'm going to multiply each side by 3. 3 times 3 is 9, 4 times 3 is 12, 5 times 3 is 15. So what I know about this is that all three sides are proportional by a scale factor of 3. Now I'm going to draw examples of two triangles that are similar by AA similarity. Again, my pictures do not need to be drawn to scale, but AA similarity says that I'm going to have two sets of corresponding angles that are congruent. I can, again, answers vary widely, so I can pick any angle measurements. Let's say this is 64 degrees. That means this one's got to be 64 degrees. And let's say this one is 51 degrees. So this angle is going to be 51 degrees. And now I have two triangles that are similar by AA similarity. The last one is to draw examples of two triangles that are similar by SAS similarity. The important one here is that the angle is included in between the two sides. Again, my pictures are not drawn to scale, and answers may vary widely. So let's say I pick two sides. Let's call this 5 and call this 8. And maybe I want my scale factor to be 5. So 5 times 5 is 25. 8 times 5 is 40. Right now I've got two sets of sides that are proportional by a scale factor of 5. I need that included angle to be congruent. So let's say it's 31 degrees. That means this angle must be 31 degrees. And then I've got two similar triangles by SAS similarity. And that concludes Unit 2, Topic 1 of the Honors Geometry exam.